The final aspect of the GMM estimation approach is the application of these principles to the model that includes both a spatially lag-dependent variable and a spatial autoregressive error term, which is called a SARSAR model in the literature. We've called it a combo model in the Modern Spatial Econometrics and Practice book. So the model, to recap, includes both a regression specification that has a spatially lag-dependent variable on the right-hand side, W1y, and for the sake of generality, we allow the spatial weights to be different between the regression specification and the error specification, where we have a spatial autoregressive model with the weights matrix W2 for the error term U. Now, in practice, there is seldom a good argument, a good motivation to have different weights for the substantive model, so to speak, with the spatially lag-dependent variable and for the error model, but in general it is allowed. So after substitution of the error term by its reduced form in the idiosyncratic error E, we get the expression on the second line with rho W1 y, the spatially lag-dependent variable, then x beta, and then an error term that has an inverse matrix in front of it. So this will have a very complex various covariance matrix. To simplify notation, we group all the variables, and again, in general, besides the spatially lag-dependent variable, this can include endogenous variables as well as exogenous variables, and then we group the corresponding parameters as well. So then the crux, the key of the solution is a so-called spatial Cochrane-Orcutt transformation, or it's a spatial filtering, where we express the dependent variable and all the explanatory variables. So this includes the spatial lag, any endogenous variables, and any exogenous variables, but not instruments. So the spatially filtered variables are then used in an expression to remove this inverse matrix from right in front of the error term. So we can express this concisely by the spatially filtered y as a function of the spatially filtered z, the theta parameters, and then the error term. The spatial lag is a little bit more complex, but mechanically it doesn't make a difference, but operationally it means we have actually two spatial weights matrices involved in the spatial lag. The estimation of this model is accomplished by so-called generalized spatial two-stage least squares, or GS2 SLS, initially introduced by Kalichn and Prucha. It's a three-step estimator. First step, we do two-stage least squares, spatial two-stage least squares, to get consistent estimates of the parameters and get residuals in the model. Then we plug these residuals into our GMM procedure to estimate, get not only a consistent estimate, but also an efficient estimate for the lambda parameter. This allows for heteroscedasticity in very general terms, the types of equations that we discussed just previously. And then the third step is again spatially weighted two-stage least squares, or S2 SLS, on the spatially filtered y and z variables. So three steps. The first step is just standard spatial lag estimation using spatial two-stage least squares. So the instruments would be Wx and potentially higher orders of the spatial lag of x. If we have endogenous variables, they will need their instruments as well, but the principle is perfectly general. We get the residuals. Now we plug these residuals into the GMM equations, and again there is a two-step process. First we get a consistent lambda, then we plug that into the weighting matrix to get the efficient lambda, and then finally we use this lambda estimate to carry out the spatial two-stage least squares again, but now on the spatially filtered variables. So this is the most general model, the combo model. In practice, as I've discussed previously, we will only consider this model in very rare cases if we cannot explain the phenomenon by a more parsimonious model that has just one spatial parameter. So this concludes the estimation of the spatial error model by means of GMM.